Hello, 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 hello. Testing one, two, testing one, two. Testing one, two, testing one, two, testing one, two, testing. Hi there.
Hello.
How are you?
Good. You?
Pretty good. I see you're in the labs.
Mhm. I haven't missed any time in the lab. Except for
Is that fortunate or unfortunate?
it's fortunate. It's the center of the universe. My universe.
Yes. I always think to myself, is that just a really nice lab at their house, or is that the actual lab?
This is the lab. Yeah, I was able to get essential worker status last April.
Oh, really?
Yeah, so I've been in the lab. I have been in the lab, all except for 8 days when I drove across the country. I drove my son across the country because I didn't want him taking a
A
plane.
plane. Yeah.
So we drove across the country and back in July. And other than that, I've been here every single day. There's very few people. I'm down in Delaware, so there's very few people around. It's actually pretty safe.
Right. I recall there only being like in a given lab space, maybe 3 people at a time.
That's right. Yeah. So what year are you?
This is gonna be 4th. So
Nice.
yeah.
Getting close, right?
Getting close. One more. I gotta finish the. I'm doing also major in EE, so
Oh wow. Okay.
extending me on that one.
That seems to be. I've got a few. Got at least one person in my 134 class who's also a double major with Dudley.
Yeah.
So what I have is I have a colloquium talk that I gave a couple, pretty recently, maybe 2 years ago, about 2 years ago, but it's still quite fresh, I think. So I don't know how. I'm willing to be derailed by conversation if that's the way this thing is going to go. It's
Right.
fine. But I'll this is my view of condensed matter actually. So because it's a colloquium, it's got some pretty general ideas in it. So.
I think it's a good transplant, especially because I know that the colloquium kind of started a beginning of understanding of physics and then grow to evolve into something a bit more complex by the end of it. So I think that's good.
Some like the colloquium we were just listening to. Today we had a speaker from University of Maryland, and it quickly got into very, very difficult stuff, even for me. I thought he wasn't. He started off by showing a lot of almost cartoonish like figures, but then he was talking about stuff that was way over my head. It was just this weird juxtaposition of cartoons and field theory,
right?
Just I don't think he was getting in the middle ground where he's actually explaining stuff. So
right.
Anyway,
I've seen a fair share of those colloquia. Let me get, could you mind checking if you do have share screen access? I want to make sure that I can.
It doesn't, no, I don't have it yet.
How about now?
Yep.
Perfect. That way I can troubleshoot all these things beforehand.
Okay, so here's my, I can put it in.
Perfect. I know it's notorious, but how big of a, I guess, a bureaucratic amount of forms did you have to do for that NSF project to do the NSF funding?
Oh, yeah, it was. The thing with NSF funding is the success rate is about 12%. So it's not that, I mean, writing a grant proposal is a lot of administrative work, but you also have to write 15 pages of what you're going to do, explaining the background and then what you're going to do. But you're right, it's a lot of work. And then to get one, we actually didn't get renewed. This grant that wasn't renewed, but the thing is, you don't expect to get funded,
right?
So you have to keep trying. So that one proposal was the third try, so successive years. Anyway, my grant right now is from the DOE, which is on the left-hand side, and it's a much lighter administrative process. Yeah.
Yeah, because every time I speak to faculty and then have them tell me about that NSF writing, it always seems like a headache for that.
Oh yeah, total headache. It's really the thing is, you go into the process and the reviewers, you know, I mean, my problem is I think my ideas are better than any of the reviewers could possibly have. You know, I think a lot of people have that.
Yeah.
Well, at least 50% of the people would be right. And you know, you get these reviews back and it's like, no, this is not what I meant at all, right? It's
Yeah.
like crazy, and you have no control over it. That's why the NSF treats science like it's a democratic process, whereas
Right.
you know there are some people who are better than others, period. I mean, you know,
some projects maybe can wait.
Yeah, right. But give me the money. Yeah, so. Well, I spent most of my career at Bell Labs, so I really can't complain. I had almost 20 years of not having to write any proposals. So that was pretty nice. But that doesn't exist anymore. I was one of the last scientists to leave Bell.
How does that decision making go into the funding of projects then when you already have a centralized fund? How do you decide, or how do you do that?
Well, we had departments, and each department had about 10 to 15 principal investigators, and they had a budget. But we had, you know, for basic stuff like helium and, you know, lab supplies, we had enough money. We just never had to think about it. And then if you wanted a more expensive piece of equipment, you make a request and it would go up the chain. It was just the company, you know, so it was managed, you know, in a hierarchical way.
All right.
But we had so few. So the thing I like to say, there was so little bureaucracy at Bell Labs that I remember once we would typically have one department meeting a year. And I remember one year our department had actually apologizing for having a meeting.
For having one meeting.
But literally like an hour-long meeting just to tell us what the budget situation was that year. And he said, yeah, I'm sorry, I have to, you know,
drag you all here.
We had no nobody knew if we were in the labs or not. It was amazing. Our department administrative assistant would always tell me, Art, you've got to take your vacation. And I said, no, I did.
For what?
I just didn't tell anybody. I just went on vacation.
Oh man.
It was a pretty wild place. But you know, the thing is you had to produce at an extremely high level. So it wasn't like a walk in the park, but at least you didn't have to worry about stupid stuff like getting simple lab supplies.
Right.
And salary, you know. Anyway, should I just start or
give me a few more minutes just to get a buffer in, and then we'll let you go ahead.
Okay.
And just so you know, like maybe I'll jump in a second or two to ask a clarification question, but I won't try and get in the way.
Absolutely. Anybody can speak up. I don't care.
Okay, perfect.
I hope people ask questions. That's the point of this, is not to have another lecture, I think, but it's to kind of have a more interactive thing where you guys are trying to learn about what doing condensed matter is like. And it's the thing is, it's completely, so our department is condensed matter and high energy / astro, and the two modalities of research are so completely different that when you said in your letter that you want to, you'd like me to talk about what condensed matter physics is, I thought, well, that's actually pretty smart thing to ask, because you won't get any sense of that at all from most of the physicists in the department.
Right.
What it's like to do condensed matter. and it's the largest field of physics. So, by a long shot.
That's what makes it kind of difficult when we hear these fields as students. We don't know whether they're just a per project or they're entire subdivisions of this field that we know to be physics. So it's good to have information on that.
Yeah. There is some organization within condensed matter into subfields, but things are really being. So I like to tell people that this is without a doubt the most exciting time in condensed matter physics in my career, which spans from the early 1980s to now. There's so many really super interesting new lines of inquiry. I'll discuss those a little bit, give you some idea of what I'm talking about.
All right. Okay, I'm gonna let us go ahead and start with just introductions.
Sure.
So hi everyone who's here. My name is Alberto. I'm president of SPS, and I'll be the mediator here. And we'll have our guest speaker. Do you prefer Art or Arthur?
Art is good.
Okay, perfect. So we got Art Ramirez here talking about, again, what is this question of, condensed matter physics as a whole. He'll share his view on it and also the research that he does to contribute to this subdivision. I think is a fair description now. Do you want to do a small introduction about yourself, and then you can go ahead?
Sure. Yeah. So I came to UCSC in 2009 as the Dean of Engineering. And then I was promoted in 2014 to physics professor. Actually had an appointment, but I started my career in the mid 1980s at Bell Labs. Right out of graduate school, I had a postdoc, and then I was hired permanently at Bell. And then I left Bell, so about 15 years later, in end of 2000, and I went to Los Alamos for a couple of years as a group leader, and then I came back to Bell. Actually, that was everybody thought I was crazy because Bell Labs was rapidly in decline, but they had no idea what Los Alamos was actually like. So if anyone wants to know what government labs are like, I have some thoughts on that too. But so then the company was doing very poorly. At Bell Labs at that time in the early 2000s was under Lucent Technologies. That was the parent company, which is basically the equipment maker for it was the equipment maker for AT&T, and they lost their business to companies that made routers like Cisco. So Cisco basically took over telecom because they understood the importance of packet switching as opposed to circuit switching. And the company went down very quickly. And by 2006, it was taken over by a French company. And we were all like told to go elsewhere. so after a year in sort of a holding pattern, I got the job here and moved my whole lab out, and big tractor trailer full of stuff. And got it. I was the first lab set up down here in Delaware, where I am. The noise you hear in the background are the compressors for liquid helium liquefaction, because I do a lot of measurements at low temperatures, and helium is the fuel that makes it go. But it's gotten way too expensive to buy and evaporate, so we have to capture it and reliquefy it. And so that's a little bit of background here. What I'm going to talk about is thanks for having me, and please feel free to interrupt as I've already mentioned. I'm recirculating a colloquium I gave a couple of years ago, but all the stuff is current. So and it gets the idea across that one of the main attributes of condensed matter physics is that we create the solid in which excitations live, excitations that are maybe superconducting or magnetic, or lattice excitations or vibrational excitations. They occur in the space of the atoms, in which are organized in a regular pattern in crystals, and it's this space that once you get to understand this as a kind of a changeable thing, that you go from different crystal structures, you have different spaces, and with this you can really have a lot of fun with predicting the various effects. And ultimately, if you're really good at this, then you'll be able to combine some fundamental physics with a device. But let me kind of describe what I'm saying. So there are basically three paradigms that constitute condensed matter, and two are very old, and one was realized recently. Firstly, the first one you say, well, of course, right? Materials properties stem from the atomic spectrum of atoms when placed on a Bravais lattice, a particular type of lattice that is periodic and in a special way. But and so, for instance, if you're talking about aluminum has this is an atomic structure diagram. These are atomic levels. Aluminum looks like that, and then from this atomic structure on the lattice of aluminum, I forget what type of cubic lattice it is, or from that you can calculate the energy band structure of electrons, the conduction electrons in the aluminum, and it'll have some form like this, where energy is the y-axis and the x-axis is momentum. So it's called crystal momentum, and it's crystal momentum because the only occupiable points in space are the atoms. Okay, we don't talk about electrons existing except when they're on an atom. You can have transition probabilities from one atom to another. But so this is called crystal momentum. It's energy versus momentum. And this really defines, this will define the properties of the material once you you can write down the Schrodinger equation, and wherever E is a function, energy is a function of K, or momentum appears, then you stick in the properties of the band structure. And for instance, you can then readily calculate the specific heat of aluminum or other physical properties. So all of this derives ultimately from the fact that you have atoms on a lattice. Okay, the second paradigm is called spontaneous symmetry breaking. So now imagine you have a lattice, and the lattice is fixed; it's not changing, and it defines the space. Well, what if you have degrees of freedom that are interacting? For instance, conduction electrons can interact with lattice vibrations, or if the valence electrons are not conducting, but they're localized on the atomic sites, then they'll become magnetic. They'll have a spin or local magnetic moment on the atomic site, and these spins can interact via various types of interactions, usually called exchange interactions. And when they interact, they can do this in a way that breaks the symmetry. The original symmetry of the crystal lattice can be broken. A really obvious example, people usually talk about the interactions leading to a potential well that's like a Mexican hat. But what happens is, the most obvious type of spontaneous symmetry breaking is if you have magnetic atoms and their interaction is not uniform, the type that wants to make neighbors point in the same direction, but that would lead to ferromagnetism, but they're anti-ferromagnetic. So right away, now you've led to a doubling of the unit cell. Before, in the high temperature state, there would be a spin on an atom, and then the symmetry of the system would be the symmetry of the lattice. But once you turn on interactions and you can get this up, down form, then that breaks the symmetry of the unit cell. That leads to a reduction of symmetry of the crystal as a whole. And one of the nice properties that I do a lot of measurements of is the specific heat. The specific heat so if you put energy energy into a sample, you'll make its temperature rise, and the specific heat is the ratio of those two. It's also the first derivative of the internal energy with respect to temperature. So you can get at the temperature where the symmetry is broken, you tend to get anomalies in the thermodynamic quantities. And this shows the specific heat. And this leads to this phenomenon of spontaneous symmetry. So it's called spontaneous. The reason it's called spontaneous symmetry breaking is it comes from the interactions. Okay, that's what that means. The interactions are such that they can lead to an ordered state which breaks the symmetry. It's not symmetry. I guess it's not symmetry. It's not symmetry breaking from an external force. It's coming from the interaction. And this gives rise to all the states that we know and love in low temperature, condensed matter, ferromagnetism, anti-ferroelectricity, superconductivity, and so forth. Now, the third paradigm is the one that's most exciting right now. It's exciting in combination with the other two. It's called topology. It's the topological classification of solids. And so by that we mean, that, well, I don't think you have to be told that an orange is different from a donut because a donut has a hole in it. And so you can deform this sort of shape continuously to look like a coffee cup, for instance, because a coffee cup with a handle also only has one hole in it. It looks completely different, but it's the same topologically speaking as a donut. Okay. And and this has led to this field of topological insulators. What a topological insulator is it's a material that is insulating in the bulk, but it has a metallic surface state because of the topological nature of the bands I remember I showed the energy bands versus momentum for aluminum. There are materials, and they tend to be materials with large spin orbit coupling, where the normal order of the bands, let me go back to that, where the normal order of the bands, so here's when I say band structure, I'm referring to energy versus momentum. So in systems with large spin orbit coupling, and those tend to be the heavier elements, compounds made up of heavy elements, you can get some reordering of these energy levels, and so it'll be a type of reordering which is sort of counterintuitive, where the S state is above the D state. That's due to spin orbit coupling, and what happens is that's all well and good inside the material, but when you get to the boundary, the energy bands have to revert to some sort of fiducial, sort of order among the, that preserves the hierarchy of the SPDF. Ordering of energy levels, and so what that means is that those levels that have been artificially inverted by the spin orbit have to meet at the boundary of the crystal, which is the surface of the crystal, and that means when they meet, that defines the metallic surface state. So that's one of the phenomena that come out of think about this topological, and when I say topological, you say, well, what's topological? What's topological is the way you determine whether a material is topological or not is you do an integral, which you can do once you have the band structure. Then you can do integrals in momentum space because you know the energy dispersion of the electrons. You can do an integral, if you do an integral in momentum space, a surface integral, and what you're integrating is the position operator. So you're integrating the position operator in momentum space. That object in trivial materials without any topological character, that integral is just zero. But in topological materials, that integral will be an integer. And that integer is called the buried space, after Michael Berry, who came up with this idea in the 80s. And so that's when we say topological, just like for a donut, there's a way of defining the difference between a donut and an orange by doing a surface integral. That's exactly the same thing in topological materials, but the integral you're doing, you do a surface integral of the curvature for the donut and orange. And for topological materials, you do an integral of the position operator in momentum space. It's kind of, you would never think of doing this unless you sort of studied this for a long time and had some great insight. And that leads to this sort of behavior that this is for a samarium hexafluoride, where for a long time people had measured the blue curve. This is resistance versus temperature, and they really truly did not understand why it was flat, because every time they made it, they would make it as pure as you possibly can make this material, and it would always just flatten off. And the reason it was puzzling is that this looks like the behavior that you might expect if you have a semiconductor that's dirty, that states in the gap. At some temperature, they provide a conducting path. But this was a real puzzle for 20 years or so, and then people realized, hey, this has the symmetry of a topological material. And then they realized, okay, well, if we do measurements that are surface sensitive and bulk sensitive, we should get a different answer. And this is what they found. In the bulk, it behaves like a semiconductor. On the surface, it behaves like a metal. At this starting at this characteristic temperature. So, this is the sense in which things have changed now. And this, if you went to the colloquium that just ended about half an hour ago, the speaker was talking about a whole slew of different types of topological families. It's just becoming so unbelievably rich, and that's why we talk about it's sort of like it's a new paradigm, because when I learned solid state physics, the surface was a problem that people just they didn't want to deal with, so they would create these artificial boundary constraints where the n+1th atom would become the first atom on the other side, and then you could do the integrals and math and it all worked out. But if you stay within that formalism, you'll never find out about surface states. So that's a really interesting thing. And oops, sorry about that. Okay, so now these topological states can also occur in spin systems. So in systems where there's no conduction electrons, all the electrons are localized, and we talk about spins on the crystal lattice site, so little interacting bar magnets on each atom. And it's also possible to get topological states among the spin excitations in such systems. And one of the real kind of holy grails of this area of topology. So you're getting the idea that topology is everywhere. Once you realize it's a thing, then you start looking and you find topology under everything. One of the first realizations of sort of interesting physics that can come out of that can arise when you what's called frustrate the classically ordered state. So when I say classical order, if I say you have now we're talking about localized electrons, not itinerant, but you can have up, down. That's a classical state because you say that's the ground state. It minimizes the energy of the Hamiltonian, but for every atomic site, the spin is pointing in a specific direction. That's a classical state. Well, Phil Anderson, sort of motivated by the field of high TC superconductivity, well, I actually thought of this beforehand. He said there's another type of state that can occur if you don't allow the interactions to mutually satisfy themselves. And the fundamental idea is that if you have a triangle, if you have a triangle and you have anti-ferromagnetic interactions, then you can't simultaneously satisfy all three bonds, because this one might be up. You'd have to put the one at the apex down. And then where do you put the other one? Because all the interactions are anti-ferromagnetic. the one at the third vertex wants to be down on interacting with this guy, but it wants to be up on interacting with this guy. So there's a fundamental problem there. It's a confrontation of the symmetry of the lattice and the interaction energy. And he was saying that there's a quantum version of that where the ground state is this fluctuating soup of spins. And then work done in 2002 showed that when you have these conditions, you get topological spin states in the spin excitations. So that's kind of what's kind of the high level view of what's happening in condensed matter. So as a corollary to the three principles, crystalline solids host spaces that don't otherwise exist. And the simplest example is the transitional symmetry of lattice gives rise to this conserved crystal momentum, and that will then define the band structure of the solid. And this notion of conserved quantity and symmetry breaking or symmetry was formalized by Emmy Noether, who basically fled. She was Jewish and she fled the Nazi regime in the 30s, came to the U.S. and died only a few years later, unfortunately. But she created what's called Noether's theorem that says a result of any symmetry that you have in a system is coupled. A result of that symmetry is a conservation principle. And so the conservation of energy, for instance, can be related to time reversal, invariance, the conservation of momentum in regular 3 space can be related to the translational symmetry of space. And in solids, we have a different set of spaces. We have a lot of different types of spaces defined by the crystal structure, and there are these associated crystal symmetries. So this is kind of what condensed matter physics is in a nutshell. We have control over our space, right? You don't normally, when you learn about physics, it falls on inclined planes and electromagnetism. The space you're always talking about is the 3-dimensional Euclidean space. Okay, but in condensed matter, we have a lot of sort of creative control over that space. We can make effective 1-dimensional systems, 2-dimensional systems with topological energy structure, and it's just a completely rich field from that point of view. And there's a lot of confrontation of theory and experiment.
As a question to that,
sure.
Sorry. As a question to that, sometimes people associate condensed matter with more of the experimental side of physics, where it's, some people have the idea that in condensed matter, you do more of a, try and fail approach to understanding what's going on in a material rather than the theory. Can you speak to why that might be the dominant thought and how that may be wrong?
So no, that's not wrong. So when we say condensed matter, we compare it to other fields of physics, like high energy. Right? So the thing is, with high energy, the experiments are unbelievably expensive. The LHC cost probably $5 billion, and every experiment is in the multiples of, like the Higgs experiment probably cost hundreds of millions of dollars. So you can't play around. The money for these experiments is given to physicists by taxpayers. In the case of LHC and these international collaborations, it's the taxpayers of many countries who contribute. So there's no room for playing around, and there's no room for setting your own agenda. You can't, because you don't have control over the equipment. So that's why when I come into the lab in the morning, I can do any one of a number of things. And sometimes I say, yeah, okay, I wonder what this system does. And I play around. I have the opportunity to develop my own hypotheses, and then ultimately set my own agenda. Whereas the agenda for science in high energy physics is set by committee. there's almost no room for originality or the ability to let your mind wander. And so condensed matter physics, we have data, but we have, the best people plan their experiments. Some of the experiments are really difficult to do. They'll take a graduate student, a year just to put the work in, but it's just one graduate student. It's not 2,000 people. So does that make sense at all, or?
Yeah, I think that makes sense. That's kind of similar to how in astro, when you want to do observation, you have this telescope, a limited resource
You have to
of
get,
time and everything.
Exactly. Fundamentally, a lot of these mysteries can be answered if you follow the money, right? So I do really cheap experiments. If I lost all my grant funding, I figured I could probably fund the research from my own pocket. My wife wouldn't like that, but it's possible. It's not impossible. And so that's another. We are rich in data. Condensed matter is a data-rich field, and it's also the other important thing to keep in mind is that it's a field with a kind of a dual constituency. There's a lot of us. I consider myself going after fundamental questions that are really rooted in theory, but there's a lot of people who work at the boundary of devices and fundamental physics, like David Letterman. I've done some devicey research in the past, but David Letterman actually makes his own thin film samples, and they can be readily adapted to a device format. And then you get to say, well, can I manipulate? Can I switch light, or can I switch a signal? And then that gets you into really interesting space of active devices that might have some importance, commercial importance. So yeah, it's a kind of, like, I should say, it's possible to do a Nobel Prize winning experiment in your own lab, and that's what Andre Geim and I forget his first name, Novoselov, did in about 2006 or 2008. They were doing what Andre Geim, they're Russian, but they had left Russia to come to the University of Manchester in England, and they were doing what they called Friday afternoon physics, and they knew that it should be possible to make graphene by exfoliation of graphite. That it was possible in principle to keep exfoliating. That means like peeling the layers off, and they literally use Scotch tape. And they knew that they should have graphene, single layers of graphene. They knew that it should be there. And what they did was they said, well, what if it's really there, but we're just not seeing it? So they said, well, how can we see a single layer of graphene optically? We'll create some interference pattern with the layer underneath it, with the silicon oxide layer. And sure enough, that worked. And they could use an optical microscope. When they put these flakes on an optical microscope, they could see the single layer flakes. That's why they won the Nobel Prize. But they won a Nobel Prize for doing work in their lab, in kind of like exploratory mode. So that's the really cool thing about condensed matter physics. You can create, and that the paper, I just looked it up recently, that their paper has about 40,000 citations. It's unbelievable. It's just incredible. And graphene is this wonderful material that has all sorts of properties that once you learn how to see it first, and then you can use it in various devices and various physics. So that's like the ultimate, for an experimentalist, that's the ultimate the sort of thing you want to be able to do, sort of let your mind wander and win a Nobel Prize in the process. So, okay, so this is my thesis experiment. It's on a material called cesium nickel trifluoride. So I did this back in the early 80s. This is the crystal structure looking looking along the looking down the B direction, and you can turn the crystal around, and you'll get looking down the A direction. It looks kind of similar. And then what you realize is that the nickel atoms, which are the red atoms in this view, are actually aligned along chains, and the chain is shown here. It's a chain. I think it's in the C direction. But these chains, you have to look at. So this is the space. This is the space I've been talking about. And when you realize how the nickel atoms are interacting via chemical bonds that go between the nickel and the fluorine atoms, which are the light gray atoms. The cesium atoms are these big green atoms that basically separate the chains of nickel atoms from each other. But you look at this at a microscopic level and you say, well, okay, I understand that the interaction between the spins is mainly along the chain. So we have a system that is effectively one-dimensional. And so this is the Hamiltonian, right? Once you know enough about the chemistry and the structure of this system, you can write this Hamiltonian where you have an extremely simple spin Hamiltonian, called the superexchange Hamiltonian, which says that the interaction energy of my spins is the this is J should be negative, so that this first term makes the spins want to point parallel to each other, like the ferromagnetic case. But this is only the interactions in one dimension. So basically the spins along the chain want to be parallel. The second term says, well, they want to. This gives them more energy if they develop a component in this. Let's see, do I have a better picture of this? No. What this says that what this second term wants to do is it wants to keep the spins in the XY plane. It says that if they develop a component along the Z direction, that's going to cost energy because A is positive. I should have put a negative sign for J here, but A is positive. That means that the picture you have is spins that want to lie in a plane but are interacting with their neighbors, so they want to be parallel. Okay, and then the third term is the magnetic field, the Zeeman term. Now, this Hamiltonian was mapped onto what's called the Sine-Gordon Hamiltonian, and this is a Hamiltonian that was developed in the context of particle physics, because you write it in field theoretic form. Well, it's close to field theoretic form, where instead of now spins, we're just talking about the angle that these spins make with respect to the direction of the field, and this lends itself to a field theory description where now you say, okay, I don't have these discrete atomic sites, but I have a continuous field theory. This is called the Sine-Gordon Hamiltonian. It's a play on words because it was preceded by something called the Klein-Gordon Hamiltonian, which was named after Klein and Gordon. And people they took the phi to the fourth term and replaced it with a sinusoidal term, and they called it Sine-Gordon. So this can be mapped onto Hamiltonian like this. And this Hamiltonian admits what are called soliton excitations. So besides the usual harmonic excitations, you can get these 2 pi twists, and these 2 pi twists are stabilized by that term with the A that confine the spins to lie in the XY plane. You need that term, otherwise you won't be able to sustain a twist. It'll unravel. Okay. So you go from a Hamiltonian of the system in terms of the magnetic excitations to something with, which is a field theory. And then what I did for my thesis was I measured the effects of solitons in the specific heat. That's my thing. I do a lot of specific heat measurements. So you went from something that was pretty prosaic, an anisotropic crystal structure. And then you took the energy of the magnetic energy, you said, we're going to consider this to be a field theory. And luckily the particle physicists had already worked out some field theories. And then we have the physical properties that can be related to these nonlinear excitations. Okay. So this is kind of, this is the way I like to see things play out. Where you have a strong you have a new material, you have a strong interaction of theory and experiment. And you can say, okay, we've observed solitons as peaks in the specific heat versus magnetic field. So,
could I ask right there,
Sure.
the reasoning or the motivation behind using specific heat as a thing to describe or the thing to investigate?
Yeah, well, everybody has their favorite measurement, and specific heat is my favorite measurement. And every measurement probes different things. The thing I like about specific heat is that it measures everything. Everything that all the excitations that can be excited are excited. And the trick then becomes how to distinguish them from how to distinguish the signature of the excitation that you want from other signatures. And that's why I plotted the data as a function of magnetic field, because nothing else in the system changes interestingly with magnetic field, whereas the soliton, I realized just sort of staring at the equations that came out that were in this paper, I realized that there should be a non-monotonic behavior. So I said, okay, this is great. So specific heat measures the density of states. So it measures all of the excitation paths in the system. Whereas if you do, for instance, resistivity is what's called a transport quantity. It has two things going on. It has the density of states, but it also has a scattering term. So transport quantities are harder to get to the fundamental physics, I think, than quantities like specific heat.
Okay.
So here's another example of a different type of space. This is a project that I was involved in the early 90s. There's this molecule called C60, which is comprised of 60 carbon atoms. Here I'm just showing the one half of the C60 molecule just for artistic simplicity. And C60 is, so this is like this is another version of carbon, like graphene and diamond. Right, this is a molecule, and then it crystallizes in what's called a face-centered cubic lattice of such molecules. And you can actually, so this is an insulator in the pristine case, but you can dope it by introducing alkali atoms. So the purple atoms are supposed to be alkali atoms, and they contribute an electron. And at half-filled doping, you get, well, if you associate 3 charges for every C60 molecule, you get superconductivity. And that's what we discovered in 1991. We discovered superconductivity in C60, which was at a much higher temperature than graphite. And this became a really, this was a very intense year. And so what happens in this, the reason the lattice is so important is that the electrons can hop, but they tend, our picture is that they tend to spend a lot of time on the C60 molecule. And so you can imagine, to go back, you can imagine this electron sort of hops into the next C60, and then it sort of hops to the next one down the line. And when it's on the molecule, it's changing its shape slightly via the electron-proton coupling. And so when the electron moves really fast compared to lattice vibrations, that's the thing to keep in mind. So you get what was called a time delayed interaction between this electron and this electron down here. This happens. The electron hops on, modulates the shape of the molecule through electrostatics, and then this electron sees that changed shape because it's a different it's a different charge distribution than all of the other C60 molecules, and it's attracted to that. This is a standard kind of cartoonish way of depicting superconductivity, but it's attracted to this region by the deformation that this electron left behind, and that's called a time delayed reaction. It's actually called the retarded interaction, but I we should probably come up with another word for that. But anyway, so these electrons pair by virtue of this electron-photon interaction, and they pair in a way that where their spins are pointed into parallel. And so this is a paradigm. This is a picture of superconductivity in general. That when the pairing occurs, it's with opposite momentum electrons, which have their spins also opposite. This is called the BCS, Harding-Cooper-Schrieffer theory of superconductivity. So this produces this pairing, and then these states they get paired into a boson. They were originally two fermions, they get paired into boson, and then they both condense into the superconducting state. And then I just use very simple formulas for such a system that describes the transition temperature in terms of an electron phonon, characteristic vibration energy of the molecule, a electron phonon coupling constant, and then this electron interaction term. And
just briefly describe why you were why that was an exciting development to find that this material could be superconductive.
Superconductivity is just a hell of a lot of fun. For it's just too much fun, because you have this you're measuring resistivity, then all of a sudden the resistivity goes to zero. It doesn't go down to a really small number, it goes to zero. And that's super fun as an experimentalist. So superconductivity, and by the time when we were looking at this, in the early 90s, there was already a field that had been developed in around 86 called high TC superconductivity. Have people heard of high TC superconductors or cuprate superconductors? This was huge. Yeah, it's really this was probably, except for high energy physics experiments, the most expensive field ever. High TC superconductivity and cuprates. We've estimated the total amount of funding for this field was in the billions. If you added up all the people that were studying, it was just terrifically exciting. And then C60 came along, which is also exciting because it was this completely different material, and it had these balls of C60 arranged in a lattice. It was just a fascinating material from a number of different for a number of different reasons. And so we showed that at Bell Labs. We showed that it went superconducting, which made it even more exciting. And there was a lot of controversy about what was the mechanism that was involved in the pairing of the electrons. There's still a controversy. There's still a lot of questions about superconductivity that are not really well resolved yet, even though we have various theories. But it's just that's my take on why superconductivity is such a fun thing to why superconductor study, why whenever a new superconductor comes along, people get really excited. I don't know, have you heard about these high pressure superconductors that have hydrogen in them in the last couple of years? So you haven't. So here's the thing about superconductivity. If you could find a room temperature superconductor, that would completely change all sorts of technology, because it would make levitating trains sort of cheap. So there's all sorts of things. If you had a room temperature superconductor, people would think completely differently about technology and materials and everything. And so for a long time, people have been one of the real sort of meta challenges in condensed matter physics is to find a room temperature superconductor. And this has consumed probably more brain cells than alcohol. Sort of trying to think of a room temperature superconductor. It's been one of the real challenges. Even now, there's a new push to find room temperature superconductors, and I think it's now gone into the topological realm. But a couple of years ago, some guys, I think in Germany, showed that if you took hydrogen sulfide and pressed on it to about 200 gigapascals, that's a hellaciously high pressure. You can only achieve that pressure between diamond anvils and hope that they don't break. But it's so room pressure. So 200 gigapascals. A gigapascal is 10 kilobars, and so a bar is the pressure we all live in, 14.5 pounds per square inch. Okay, that's one bar. 10 kilobars is pretty high pressure, right? 10 kilobars is 1 gigapascal. So then multiply that again by 200, and then you can make hydrogen sulfide go superconducting. And it went superconducting at about 250 degrees Kelvin. So getting close to room temperature. But it's completely useless because you can't have any reasonable device work at 200 gigapascals. But people are still trying. And what makes that work, if you go back to this equation, you can see the electron phonon, the characteristic phonon energy comes in as a prefactor of the exponential. So people have been looking for hydrogen-based superconductors for a long time because hydrogen should have an extremely high phonon frequency because it's really light, and you can get a strong hydrogen bond, and so you can get very, very high characteristic phonon or lattice vibration frequency. That's why people are looking at that. Anyway, so so these are just some of the things I've been involved in. What do we have? We're going to 6, right? It's 5:50.
Right.
So let me just finish off with what I'm best known for is a field called geometrical frustration. And this started with, so this paper by Gregory Vanier, who was at Bell Labs in 1950, showed that you can have systems, triangular lattice systems, and here's the cartoon that I used to illustrate what I used my hands for before. If you have anti-ferromagnetic spins on a triangular lattice, you can't satisfy all the bonds if you stipulate that the spins can only point up and down. And there are systems where that's a good approximation. Whereas for ferromagnetic bonds, you can get a minimum of energy when all the bonds are satisfied. Well, the important thing is not that the ground state is at some energy, but the important thing is that the entropy is finite at 0 temperature. And that's not allowed by the third law. Do you remember that in StatMech? So, so this is kind of a hint that you're going to find some interesting physics in systems that are geometrically frustrated. Let me skip to the, there's one interesting lattice that Shriram Shastri, who's here, postulated in 1981, and that's another type of frustrated lattice. But what I did was, let me not go through this. The thing is, you want to look for structures, and so the importance of geometrical frustration now is that these are the materials in which you would be looking for quantum coherent states that might possibly lead to a quantum computer, if you can learn how to manipulate this quantum spin liquid. You want to look for, from a materials perspective, you want to look for states with materials with, so you want to look for materials that have a triangle in them, that are built out of triangles. And it's actually, there are a lot of crystal structures like that. For instance, there's this triangular, two-dimensional triangular structure. You can find this in what's called the space group P63MMC. So, you know, the set of all possible crystal structures are delineated by what are called the space groups. This comes from group theory. It dictates all the possible ways you can configure atoms in 3 dimensions. You can also get in 2 dimensions what's called the Kagame lattice, and what distinguishes the Kagame from the triangle is that the triangles only share vertices, not faces, and so this ends up being a much more frustrating type of structure. And again, frustration is when you can't get all the bonds satisfied, and you'll get things like 0-point entropy. And so what I did in the 90s was I sort of codified this field. I said, you know, there is a class of materials where we should look for interesting sort of collective effects that are unanticipated by the from the classical methods. And so there's 2-dimensional ones, there's 3-dimensional ones, and these are all mineral classes. So there's, you know, you can find materials that have this triangle at their base, and so this is, well, I won't get into this. So let me just say, so again, I said what the important thing is not that the temperature, the ordering temperature is lowered to some very low value, but that you have this degeneracy. And let me just show you the one experiment that I did. This is called, yeah, it's called a Kagame net because it's called the Kagame lattice, this corner sharing triangles, because it's the type of Japanese basket weave. And let me just show you, but there's another type of frustration. This will be the last thing I talk about. So it turns out that there was a problem in the 1930s. There were groups who had measured the configurational entropy of water at room temperature. And they did this by measuring extremely accurately the rotational and vibrational modes of the water molecule using infrared spectroscopy. And then there was another group who measured the entropy at room temperature by integrating the specific key from helium temperatures all the way up to room temperature. What it really impresses me is the accuracy of these measurements back in the day. And what they found was a discrepancy. And Linus Pauling, the very famous chemist who won a Nobel Prize for chemistry, but also a Nobel Prize for peace, he showed that this discrepancy in the entropy can be explained by stipulating that the hydrogen, so this is a picture of ice, this is what's in your freezer. What ice is a material where the lattice is ordered. So all the oxygens live on a perfectly ordered lattice, but the hydrogens are completely disordered. They can adopt, you know, they can't break the H2O bond, but the H2O orientation can be one out of, it has 6 different ways on every atom. It can be in 6 different ways. Every oxygen atom, you can have the orientation of the bond be in 6 different ways. And that gets frozen into the system at low temperatures, and such that you have this ground state entropy. Well, we found a magnetic system that behaved like that. It's called the spinel or pyrophore, where you can map the hydrogen degrees of freedom onto spin degrees of freedom. And I did this measurement in 1999, where I showed that you don't get all the entropy out of the system. So spins are great because they can have low energies where all the other excitations are frozen out, and they have a fixed amount of entropy. It's a spin and a half can be up and down. So all the entropy you get out is R log 2, where R is the gas constant. And I measured the shortfall, and that shortfall was extremely close to what Pauling predicted for ice. So this material also violates the third law. So, you know, you can see, I hope that in these examples, I've shown you the ability to ask very simple questions and then find spaces and materials in which you can possibly answer those questions. And it's just an extremely fruitful, fertile field for an individual experimentalist to get involved in. And then ultimately, we haven't gone into any devices or anything, but it can get really exciting, for instance, when you're talking about topological materials as devices. And one of the things I'm working on really closely with Sergei Sidranov, who's a young theorist in our department, is there's actually a topological principle in geometrical frustration. We've just realized this in the last few weeks, and so we're pretty excited about that. So you see all these threads coming together right now in condensed matter physics, and it's just unbelievably exciting. Period. So with
Well,
that,
thank you. Yeah.
so that's, so any more questions?
Let's see. If you have any questions, you can feel free to unmute or chat, whichever one. While we wait to see if any of those. Thank you for coming. I really appreciated it. And it's been greatly informative when I hear these terms again and again. It starts to settle, and that's been good. Degeneracy, I think, is the one I've heard the most whenever I talk to condensed matter physicists, and I think it's great to hear again. Okay.
Yeah, I'm sort of, as you can tell, I'm kind of evangelical about this field, because it's actually my own career is sort of when I started off as an undergraduate, even in the first year of graduate school, I thought I might want to do high energy physics. Then I realized, I'm really not good enough at math to do theory, and I don't want to go to one of these accelerators, on the other side of the world. It's a hard way of life. And I'm kind of lazy. I just like going in, I like going in the morning, okay, doing my thing, and then going home and just, like having a regular life. From that point of view, I work all the time, but from that point of view, I'm just like kind of a sissy in that sense. Or I'm not I'm just kind of like, I like my creature comforts, let's put it that way. And I hate flying. But I had this fellowship from Bell Labs, and I didn't even know what Bell Labs was at the time. But I got this fellowship. Some person called me up from Bell Labs and said, "Hey, are you interested in applying for this?" And I got this wonderful fellowship. And then I saw, let me look into solid state physics. It was called solid state physics back then. And so that was my path. And then I went into solid condensed matter, only interested in fundamentals, and then I got more and more interested in devices as my career progressed. And I've done some research in field effect transistors as well.
It looks like we have a question. Yes. John?
Oh,
hey, Art.
yes.
Yeah, I remember when you used to talk about the measurement problem, right? Like the theory of a measurement and stuff.
What do you mean?
I remember I don't know, it's like years back when we chat, and I think you mentioned this idea of a measurement of related stuff, because I think I'm getting more to like mathematical physics. So there's the idea of a measurement in quantum mechanics, that there's the issue of a measurement, right? Like,
are you talking about non-local?
Yeah.
Because if I talked about a measurement challenge, then I would have been talking about measuring non-local behavior.
Okay.
So that's actually, you're driven to that by thinking about topological systems. Because the physics of everything I've just, all the non-topological physics is defined by the microscopic degrees of freedom.
Yeah.
And so you say, the simplest case is you have spins, and then you construct a mean field model where every spin is looking at a mean field, which is basically set by its neighbors, right? So everything is determined microscopically. But topology brings in another twist where you have to really consider the boundaries. And so, clearly, if you just put two contact pads to measure resistivity on a sample, you might just be measuring the surface conductivity, right? It has nothing to do with the bulk. That's one extreme limit of that. But by what we're trying to do is trying to set up a measurement scheme where we can test for whether you have a topological state or not, in a kind of model independent way. So that might have been what I was talking about. But
because of what I was thinking, I don't know if it related that much, but it's more of like the way of can you study quantum system without ever needed classical mechanics, right? Like as a human being, we are classical objects. So can you actually truly understand quantum mechanics and the measuring actually correspond to what happened in the system, you know.
That's beyond my pay grade. I don't understand. No, that's a very deep question.
Yeah.
And actually there's what you'll find for those students who want to go into quantum, like, quantum problems, for quantum information, say, is that there's a whole field of quantum physics where the language is completely different.
Yeah,
I mean,
it is. Yeah.
I read terms that I have no idea. Like,
Yeah.
One term is fluffy bunny.
Yeah.
Fluffy bunny. What the heck is a fluffy bunny? Right?
Yeah, I know the quantum information people, they use kind of sort of different idea.
It's crazy. Yeah.
They don't take a state as an element of Hilbert space. They take state as a linear functional on the bounded operator, which means you never have a you treat observable or operator, the measurement as fundamental. The state is some sort of byproduct because you only measure and then you get stuff. That's what quantum information people mostly think about. But I think in foundation of quantum mechanics, it's trying to connect like the idea of observable in classical mechanics and the idea of observable in quantum mechanics. Is there a natural way to pass through, the boundary? Because the classical, like, the quantization, canonical quantization is flawed, right? Like it's not always working. And actually the physics behind it is, the math or physics behind it is ignored. It just said, well, we have a commutator and that's what governs our system. Yeah, but how do you pass from a Lie bracket?
I have no idea. Yeah. Look, what I do is I take little samples and put small amounts of heat in them and measure the temperature. I've been incredibly successful with that simple approach. But no, but the thing is, I measure entropy, and I was in terms of these terms, I've heard about entanglement entropy. So it's the entropy that's involved in entangling in making a system quantum coherent. And I've asked theorists, like every theorist who knows anything about this, so how can I measure this? And no one has a good answer.
I know. Actually, for the entropy, I think there's a model, a theory called like water drop, description of like entropy, which related to a fancy mathematic called C-star algebra. and I was looking into it. It's kind of like not really much people,
Well, if you ever find a practical realization, I would appreciate if you told me.
I'm probably gonna send you a talk or something, but I don't know. It's very theoretical. But, and also the other question is the topology you talk about here. Every time you mention topology, right? Like you more think of like the underlying topological structure or the underlying geometry, basically how many holes you have, right? Like, that's what usually, but actually there's.
You should ask, what's the conservation? What's conserved?
Yeah.
Right? What's the conservation law?
Yeah, and there's actually a deep problem is that there's no way, if you don't consider extra structure, there's no way, not no way, probably there's a way to equivalent like to topology. Because there's too many things to consider. So
that's why it's its own paradigm.
It's so how in the field of topological material, like you
there's no one procedure for finding topology. I think it's because you have to first of all you have to have really good confrontation between the materials and the theory, and that's actually becoming a problem because you do need a very high quality material in order to get a clean band structure in the bulk. And that only when you have that high purity, then you can see the surface state. But that's a problem because people who go into physics these days don't understand how much work was put into making silicon pure. It's just a terrifically hard thing to make any material pure. You have to really think about what's happening as it's melting, right? And just figure out. So it's gonna, that to me is one of the big building blocks. You see all these talks, like the theoretical talk today, there's